So I just have a couple of slides I want to go through before we get Steve started. Of course, this is Steve Holmes will be presenting on IP 101 for the operator and engineer. I thank our Sacramento SMPTE board. Some of them are here tonight. Always appreciate all your volunteer time to put all this stuff together. Wanted to remind you that SMPTE elections are underway. You may have gotten an email. Some of our positions, chair, secretary treasurer, are 1 year positions. So we have to re-elect them each year. And then 3 of our section managers get re-elected each year. So you'll see that on the election ballot. SMPTE's announced that they've made all the video, or at least the top 100, videos from the SMPTE 2020 Fall Technical Conference available for free right now. And it's available till the end of the month. So that might be something worth checking out, see what was presented and get access to that. Also, until the end of the month, they have a special on membership. You get 20% off if you use the code word video. All right, I'm going to introduce Steve. I'm going to quickly read his bio. Steve has over 35 years of video application engineering experience. He is currently working as a solutions architect and application engineer for Leader, focusing on SMPTE 2110 IP video, PTP, monitoring, 4K, HDR, and video test solutions. Before coming to Leader, Steve was a senior video application engineer for 21 years with Tektronix, consulting and teaching test methodologies for 4K, HDR, SMPTE 2110, PTP, broadcast, studio, cable. It seems like a pretty wide range of things there, Steve. Like everything, yeah. Manufacturing for customers based in the Western United States and Western Canada. Prior to Tektronix, Steve worked for GTE Verizon for 20 years, teaching, engineering, and managing video and CATV systems. At GTE Verizon, Steve was involved in one of the first video on demand, near video on demand, fiber to the home, fiber to the node, and hybrid fiber coax trials before the development of digital video compression systems. So quite a career, and very happy to have Steve here tonight.
Thank you very much.
Steve, I'm going to stop sharing and let you take it from here.
Okay. Okay, hopefully everybody can see my screen. Thank you, there, Bob. Okay, so come on, computer. There we go. The thing about the I/O interface that we need to remember is IP is just another I/O. It's just another way to get video, audio, and data from a switch or a device to another point. It's just still an I/O. Some of the things, though, we're used to looking at, like an SDI, we used to look at, levels, we'd look at jitter, we'd look at eye patterns, we'd look at EAV, SAV placement, CRC errors, and then possibly pathological issues that would creep in from time to time. In IP, it's very similar, but now we're going to look at optical power levels. We're going to look at CRC errors, RTP errors, packet spacing, and then we need to know what a switch does with corrupted packets, because it is a little unique. And it's just how we do that has changed. So what we do really hasn't, it's just how we do. It's still getting signal from one point to another point. So I'm just going to take a real quick run through some of the basic parts of things here. 2110's been around for a few years now. I've worked on it since its inception. It deals with breaking the video down into essence or flows. So we end up with a video flow, audio flow, and a data flow. So, and in the video, it is only the payload data. It does not have any of the vertical interval or horizontal interval with it. Any of the data that would be in that area is carried in the -40 stream. So SMPTE has broken the standard into subparts of 2110, -20 for video, -30 for audio, -40 for data, and there's several more in between all of those they've come up with. The 2110 standard uses PTP IEEE 1588 for synchronization. Now, PTP has actually been around for many, many, many years. The entire cell phone network is tied together using PTP. The handoff from cell to cell to cell is all based on RTP timestamps with PTP. The entire stock market, when you make a trade, it is timestamped using PTP. So PTP's been around a long time. The problem initially with PTP was it didn't know anything about video. It didn't know anything about framing, about color, about time code, about any of that stuff. So SMPTE then introduced the 2059-2 profile to add all of the stuff that we all know as video parts into PTP so that we could actually have a receiver be able to get that particular data. So the thing to remember about troubleshooting, though, in a network is really nothing's changed. It's still a divide and conquer. You still end up going into the middle of a network. You want to look this way or this way, and you cut your network in half. If I'm looking to the left and everything's coming in just fine, I know it's the right half of my network, and I've already cut half of my work down. The other thing is you can use IGMP, which is a thing that you can do with multicast flows where you can actually have the receiver, you can put in a multicast address, tell the device that you're working with, in this case a waveform monitor, to join the flow, and if it's a conventional IP switch, you can use IGMP to join that flow and bring that flow into you so that you can test. If it happens to be a non-conventional IP switch, you may have to go over to the router panel like normal and route the signal, or use NMOS to turn around and route that signal to you to be able to test. But also in this day and age, we're going to have a lot of SDI to IP conversions, a lot of IP back to SDI conversions. And it might be a nice thing to be able to look at both the SDI side and the IP side at the same time, because things might get lost in between things. So one of the features with at least the Leader product is I can look at multiple streams together at the same time. So on the left-hand side here, you're looking at the SDI flow that is getting converted to IP, and I'm looking at the IP flow on the right-hand side. This can be incredibly handy at looking at things like right here. If you look at this flow right here, something's wrong on the right-hand side. So on the left-hand side, it's my SDI feed. The right-hand side is my IP feed, and no captions. So it really can help being able to do true hybrid in this day and age that we're in, where we are converting things that, boom, you know, right off the bat, my captions aren't getting through. You can also look at, you know, multiple waveforms on the left-hand side. That one's set at PQ. The right-hand waveform is set for 709. You can do multiple gyrations on each side. The other unique thing a lot of people just started thinking about is, what about audio delay? And I'm not talking packet delay necessarily. I'm talking the payload inside the packets. The packet should be stamped with the RTP timestamp from PTP, so we know where to put them back out. But when things got converted, where did the audio happen to slide? So this is actually a real shot off of my little office network here. And this is my SDI coming in, and there's absolutely zero offset. When I went over to my IP side, I could see that my audio was advanced by 46 milliseconds. And luckily, in my little box that I'm running right now to convert this, I was able to actually go in and pull the audio into only being 4 milliseconds off. So, which is totally inaudible. Nobody would ever know. I'd say probably most customers wouldn't know 46 milliseconds, but most of us that work in the industry can see it. But it's something that you have the ability to actually be able to do AV delay across SDI to IP back to SDI. And how did it come out? I mean, we fight enough with what OTT and cable companies do to us with AV offset and decoders. We don't need to start our network off with having issues doing this. The other unique thing is timing. Since we only send the active part of the picture here, when you look at where the video is relative to PTP, you're going to see the offset of how far down the active video is. So if you look in the side here, you're going to see 21 lines off because this is 1080i, and the active portion of the video here starts 21 lines after the very first pixel in the very first line. So PTP, though, actually starts at the same place Blackburst would start, which would be at line 0, pixel 0. So PTP's 0 point is actually at the very beginning of the entire package, not just the beginning of the active raster. So PTP should be in perfect alignment with Blackburst and tri-level, but you should have an offset of both the number of lines down that the video starts and the horizontal increment that's going to move it over. And you can actually see that in this particular display. Here's the shot of my little network here, looking at where is PTP relative to NTSC. Because let's face it, PTP needs to be synchronous to the rest of your house because you're pulling your video in from the rest of your house. Different devices, especially measurement devices, some of them FIFO the video and don't care where PTP is. But any device that you have that is going to act upon this video, have to manipulate the video or audio, is going to have to care where it is in time. So you need to be careful when you're looking at some devices, because especially monitors and things like that, most of those just FIFO the signal and don't even care where the PTP timestamps are. And as a packet comes in, they bring it in and throw it up on the screen. We can look at the timing of two inputs. So a standard that I didn't put in here that a lot of people know about, though, 2022-7 is a 1-for-1 protection switching where it's a packet picker. You send two streams of the exact same data, goes into a little device, it's got a small buffer in it, and it's looking at the RTP timestamps of the two packets. If you take an error, it just grabs the packet from the opposite stream and the output stays absolutely perfect. And I'll talk more on this in a little bit, but you can also then look at, you can see port 1 and port 2, their timing. If you look at the average there across them, the video from my primary, what a lot of people would call your red network and your blue network, are exactly the same. And then the audio offset is exactly the same. So that you can look at that your protection switching is going to work because the two streams are in close enough proximity to each other for the packet picker to be able to grab the packets from the opposite flow. Here's a unique condition that I've had happen more than once. If you look at the top up there in the little yellow box, no signal. But yet I have a port 1 video flow at 1.3 gigabits. I've got audio at 9.65 megabits. I've got video at on port 2, the same, but absolutely no decode. And if you look at the port timing, there's virtually no port timing. The RTP timestamps in the video and in the audio in this case are non-existent. So it's going to be very, very rough to decode this. So even though the waveform monitor actually was able to do an IGMP join, or in this case I actually used NMOS, and sent the flows to the waveform monitor, absolutely nothing was decoded. And it's absolutely because there was no RTP timestamps that were detectable within the audio or the video. The same thing would show up trying to look at where's the PTP to RTP offset. It can't find the RTP timestamps to even tell you where they're at. So it's a lot of different things that we can look at within this. So if we just kind of take a real quick jaunt over here for a second, should be seeing actually my 2110 stream here. I'm looking at audio, looking at video, all the normal stuff. But I can go in and look at several of these pieces. If I go into my stream here, go in and look at, there's the flows from the streams. I can go in and look at that timing comparison chart, and you can see the timing between the port A and the port B are absolutely spot on with each other. I can also look at, I actually have, get the right mouse, 2 different streams. I can look at the second stream and look at its offsets. So I have the ability to look at multiple things through my system here. We can, not that this is a complete PTP thing here, but I can look at my timing, make sure that I am locked, make sure my T2 minus T1 and T4 minus T3 timings are good, which is the time that it takes to get from the PTP generator to me, and the time it takes to get from me back to the PTP generator should be almost identical times. Say my network is very symmetrical. You don't want those offset from each other any great distance at all in looking at this stuff. So if I go over here and I go to my A input, let's go to a different screen. So this is our AV delay sequence. So you can see the bar go by. When it hits the center, you'll see a white bar show up on the screen. And we look at the coincidence of those 2 events and can actually turn around and measure those. And you can see that it is absolutely 0 offset on my SDI side here. If I go to my IP side, let it sync for a second. One unique thing is it had 8 channels on the SDI, but only 4 of them are getting encapsulated. It's another minor issue I've got, that I lost 4 channels in the encapsulation, but I've been able to dial that down to one millisecond offset. And I have the ability within the encapsulator device I've got to be able to actually move that to where I need it to be. The other unique thing that I showed you just a second ago was if we look at the external phase here, you'll see that I am looking at my IP input C. I do have a 21 line offset. You're never going to see that perfect 4 microsecond offset for the horizontal interval, but it should be absolutely dead still and looking like this, not moving. If I look at the reference of where's PTP to my NTSC, so I've got black burst going into it, I'm 0 lines off and 0.2 microseconds off. So effectively 0 by 0. So my PTP and my black burst are absolutely timed with each other. The thing you don't want to see is, let me go to my A input and go to the same screen. That's not you. You silly man. Going to the wrong screen. Sorry. This is what you don't want to see. This is an unlocked source. So my SDI-A is coming out of a little player that has no gin lock. So I've actually had to run this input into a frame sync and frame sync this so that it will come out virtually perfect when I look at my IP of the same input here. Oh, I keep picking AV delay. It's what I was just talking about. External reference. Silly. So there's the exact same thing there. And the other thing I have the ability to do here is also, like I said, be able to look at both of those 2 inputs actually right next to each other. So there's my A and my C. I give something a little more interesting as video. You can watch those and you can actually see the A over there with its input time wandering all over the place, and the B on the right hand, or the C input, which is the IP of that same input, absolutely stable. So let's look at monitoring physical layer errors here. So in the IP header, when we look at an IP packet, we can actually see the Ethernet header, we've got the IP header, the UDP header, the RTP header, and then where the payload is, but there's a frame check sequence, which encompasses all of that, the FCS, which is just a checksum error of the entire IP packet. And if you take an error in an IP packet, you'll have a frame FCS errors, frame check error. One of the problems, though, is if I'm looking at switches and I'm going through and all of a sudden I take an error coming out of that switch, I will have those FCS errors, those packet errors, coming into the next switch, but I will not have those packet errors leaving the switch. Now the switch has no way to magically replace that packet because it's video, and by the time it got there, that video is gone and doesn't exist anymore. So we do have a data loss but we don't have packet errors anymore. A switch or router will drop the bad packet. So it's part of the IP standard that bad packets are not propagated through the network. And there's actually a really, really good reason for this. If you think about it from just a raw data perspective, and someone is dropping your paycheck, and you're getting delivery to your bank, and all of a sudden somebody takes a packet error and they drop the most significant digit off of your paycheck, you wouldn't be very happy. From a video perspective, you might change the multicast address of that video. And all of a sudden, little Johnny down there that's watching Sesame Street, all of a sudden gets a flash of the whoo channel and goes running to Mama and goes, "Hey, Mommy, what's going on?" So we need a different way to be able to look at this. Also, one dropped packet is incredibly damaging to the video we're looking at. One packet is about a quarter of a line of 1080 video. It's a lot of data. This is where we get into the RTP header that we've added for real-time transport protocol here. It has a sequence number in it. Very similar to what we've done with MPEG with a continuity count error. It is a 16-bit field, much larger than MPEG, but it's a sequential count. Each packet for that particular IP is sequentially numbered. And that number transverses the entire network. So if we look at that number and we look for that number to sequence by 1 each successive packet, we can turn around then and do the same thing, but now look for RTP sequence errors. I get that same data hit, and right now I've got no RTP errors anywhere. I get that same data hit. I've got those FCS errors going into that switch. I've got no FCS errors leaving that switch, but I will have RTP sequence errors leaving that switch. So we need to look for those RTP sequence errors in order to see and be able to look at what the health of our network is and whether or not we're sending bad data through the entire network. We still have the data loss. We're still going to have some really nasty video if we aren't doing something else to protect it. The other unique thing that's starting to happen more and more is we're getting into places where we may have a video flow and an audio flow that are actually starting on 2 different networks and going to a switch, going to something, i.e. maybe it's a switcher, and being put together, and they come out as a single flow. Think about trucks. You've got 20, 30 videos coming in. You got the talent doing voiceovers, and they're switching all these videos under them, and they're all coming out on a single flow as a single video with that audio now coming out. So if we take that same error and I have those packet errors, it's just on my video leg, but now it's on the same path as everything else. So now you may have errors coming out that are only related to just the video, and the audio is perfectly fine. Now that should tell you exactly where you need to go back and look. Where are those 2 separated from each other? Because the only way that can happen is when you have the 2 separated. They both will take errors. Now, your video's always going to have more errors than your audio path is, but they're never both going to be untouched, because your video flows about 15 times bigger than your audio flow is, if not more. This is where we get into a little standard called 2022-7 you may have heard about. Most of you know about it. That's our little one-for-one packet picker. And especially from sports venues, it's not uncommon to have a primary and a backup. Everybody's been calling them different colors. So in this case, it's my red network, my blue network. And I've got no errors leaving the venue right now. But all of a sudden, I take an error on my blue, and I'm taking RTP errors. But my red network is still fine. So the output of the packet picker is still going to be absolutely perfect going through the rest of my network. But you need to know that your network is degraded, that you do have errors. And it's something you need to start looking at, because if something happens to the red network and the errors fall at the same time the blue network is, you are going to have issues. Same thing if you continue that red and blue network all the way through your leaf spline, you could have the same thing, that all the way through your leaf spline, you've got those same errors going through the entire network. One side's got an error, but almost all devices that are hanging off of this, if it's 2022-7, are looking at the output of that packet picker, and it's giving you a perfectly good flow. And you need to know to look for those errors and be able to watch out for them. What does this all look like when we look at it? I have found this out by just working with many customers, many different devices. Everybody builds their picture differently off 2110. It's not like MPEG, where MPEG sets a raster size and you basically have the raster and you fill it with variable amounts of data. So the raster is always there. In video, even 2110, it's still line by line. We still make it. So if I drop a quarter of a packet in the left-hand picture, it's kind of hard to see. I'll show you some enlargements of this. But about halfway through Lady Liberty there, we took a hit, and the picture from that point to the bottom all shifted to the left by that one packet, because every other packet is going to fall in line, and now all my TRSs are in the long location. The picture in the middle got all kinds of little stripy lines through it. The picture on the right absolutely went bye-bye. So there's the one, and you can see the quarter of a line shift. So this was one RTP error. And that one RTP error was right in the middle of the picture, and everything from there down to the bottom for this one frame was off. The next frame was absolutely perfect. But when you're taking random errors, the frame sits there and it jumps left, jumps right, jumps left, jumps right. I just happen to be able to capture this one frame and capture that one error on it. On another device, it kind of made the raster, so the raster was always there and it was laying the 2110 data into it. And so you got all the pixel errors instead. So you can see those, hopefully it's coming through on the Zoom. You can see those little stripes across the big buck there where there's different errors happening. And then there's the last case where once the TRSs disappear and I don't have my sync anymore, my EAV, SAVs, and they're in the wrong place, there was no way to frame anymore. So once the error hit, the picture went black. So you take that hit, and if it's halfway down the picture, you lose half the picture. If it's the top of the picture, you lose the top of the picture. That is really nasty. And it just depends. And that's how a lot of processing equipment is going to grab it, because it's going to be looking for the TRSs, and all of a sudden the TRSs are in the wrong place. And you're going to lose framing for that frame and have to start over. So this is where having that 2022-7 can really, really help a lot. So within different waveform monitors, different ones put different errors up in different ways. This is the screen, of course, off the leader. But you can see that I only have the A link up on this one, or link 1, but you can see the FCS errors. So that's looking at the direct frame errors there. And there's both link 1 and link 2, where I don't have any errors on either one of them. That's looking at all of the yellow here. You can look at the IP header checksum, UDP checksum, and the frame check sequence, and making sure that those are all good going through the system. And if one of those is bad, you'll get a red glitch across the bandwidth screen indicating that particular error happened and how many of those errors you've had. But you have to be on the actual fiber link that's actually taking those specific errors in order to be able to see that. What you need to be able to look at is the RTP error sequence, which is off of the packet arrival time when we're looking at how clean is my flow. And this stream was having all kinds of issues because it should be a nice, consistent top here and not all of these really, really late packets. And then the RTP errors that are happening through the switch. So this is the stuff that you're going to be wanting to look at first to look at things. Here's one, and this is actually, both of these shots are off of a real network, if you can believe that. So this was stuff that I caught at a real network someplace. It was pretty bad. The other box that we deal with, which is the Phabrix, it will show the sequence errors on the same line that is showing you what videos it's looking at in the bandwidth. Over on the right-hand side, it'll actually show you the RTP sequence errors and tell you when you have RTP sequence errors and how many you've had. The other thing that we can look at and see here is looking at, this would be almost akin to looking at eye and jitter, but not quite, but looking at what is the quality of my optics coming into me. In this case, in port 1, I've got a 25 gig SFP, and my receive power, don't really care what its transmit power is, but I do care about what its receive power is. And what I've found is if this receive power on a multi-mode unit gets down about -10, -12, you're getting where you're losing power. My port 2, I happen to have a 10 gig SFP in it. So I can only go 10 gig because it switches both ports. But if I'm only going 10 gig, it didn't care what it was on the first port. But you can see it's coming in about -3.57 dBm. You want to be able to look at that and be able to see what's going on here. So if we go back and take a look here, just a second. So this is the Phabrix QXL here, and up here would be the sequence errors that we're looking at. The only way you can see FCS errors if you're on the fiber that's in trouble is you have to look at packets and good packets, and you should have the exact same count. So you'll know you're on the link that's in trouble when you start getting the sequence errors and you start getting a count mismatch. You can also look at the timing of the video. I only have one port running on this guy right now. I don't have enough ports in my poor little switch here in my office. But it gives you that same timing diagram that we had going on before with everything. And does give us the video and audio monitoring. If we get out of multi-screen here and go to here, and go back. Wrong mouse. Wait one on our mouse. All that junk off the screen. And you can see I've got some RTP errors happening. So my network in my office is taking sequence errors. So anytime those would have come up, I would have had some type of glitch in my picture, possibly, if it happened on both my C and my D input here. So if I was looking at both sides here of the input, and I have purposely done this. What I've got is a little itty bitty, it calls itself a 10 gig switch, but I found that if I put more than about 4 gig of data through it, it starts randomly dropping packets. So I can go back and actually look. So this is the last hour, how often it's dropped packets in the last hour. There's the last 2 hours. If I drop one of my services off of this thing, it goes absolutely perfectly clean. But I put it in line so that I could show you these same sequence errors that I am getting in being able to look at this stuff. So I hope that this has helped some. And let me go back to one thing real quick. Go up here, go to my next window, look at my SFP data. So there's my receive power coming in to port A here. And you don't see any receive power in port B because port B is a copper pigtail. So there is no power. I've got a copper jumper on it. And if I look at correct, so if I drop this guy to where I start, whoop, 21, definitely went way past it, minus 21 dB on power. So if I go back to look at, since I was playing with the input to my measurement device, I do see those FCS errors now. But up until here, I've never seen any of those RTP FCS errors. All I've seen is the RTP errors because they're happening one switch back. I've got 2 switches in tandem, and the first switch is taking errors. The second switch is not taking errors. So just to kind of wrap up here a little bit here is, again, IP is just another interface. Yes, it does take some learning, but it's still doing the same thing that we did with SDI. It just got a few more little pieces to it. If you do have 2022-7 1-for-1 redundancy, you need to think about checking both sides of the flows when you're running your network, because your gear may not tell you that one side is taking errors and your video is absolutely perfect. And again, if you're getting errors only on a video network or only on an audio leg, the only way that's going to happen is if those two are separated at some point through there. And no picture or picture breakup, you know, like what I had with that screenshot, because that was actually a screenshot that I had. The RTP timestamps just were not in the video at all, or audio. And it's still, you know, divide and conquer. Go to the middle of the network, go look at it, and see what we got. So I hope that gave some little bit of insight to some of the real world things that the guys out in the field are going through and having to deal with on a day-to-day basis. And welcome if anybody's got any questions at all about anything. Come on, Gil, you're never one to be quiet.
Hey, Steve, I have a question, actually. I have a bunch, but let me narrow it down. So when you say,
hey, Alan.
So when you say look at it, pick it in the network, do you mean actually taking a physical patch between your switches?
Well, no, you can route I mean, if you're just looking for the RTP errors, all you need to do is route it to your waveform monitor, and you'll see the RTP errors, because if they're on the path, you're going to route them, and you're going to route them to yourself. So however you do an IGMP join, you get an NMOS and tell NMOS to do it, you go to the router control panel and send that flow to your waveform monitor. It's when you get to the last point, you see errors at, you know, this point, you go 1 point back, you don't see the errors anymore. That's when you take the fiber out of that last device, put into your waveform monitor, and you'll see those FCS errors now saying, yeah, this is the link that's actually in trouble. And in a lot of cases, especially on new builds, if you're using QSFPs, it's not that uncommon that a QSFP is either dirty or misaligned, and it may just need to be pulled out, cleaned off, and put back in, because there's a lot going on. You got 8 fibers in that one little itty bitty connection.
Yeah, we've run into that a lot with MPO cables and dirty fiber. Can you talk a little bit about, you know, when you talk about these errors, about, you know, where do these errors occur actually? And what's causing them?
That is a lot of different things. One is that dirt on the fiber. You know, if it is a QSFP, and that's going into the next switch, by the time it comes out of the next switch, it's just going to be RTP errors, and you'll be trailing those. But in several cases I've seen is oversubscription of a port or oversubscription of a switch, putting more data than the switch can actually handle. You know, most data people will tell you they don't like packing a switch more than 80% on a port. So if it's a 10 gig port, you put 80% of 10 gig, and that's as high as they want you to go. A lot of people in video are trying to get more than 90 off the switches, and some like it, some don't. But you know, the thing about video is it's not regular data, it's continuous, it never stops. You know, most data networks, you know, it's very bursty, and things are going on and off, so there's time for switches to do things in between. With video, you know, a lot of them are 3 gig flows, and they never stop, they never go away. And you've got 6 gig going to that one service if you've got -7 running. So, you know, you can have a bad SFP, you can have a dirty SFP, the switch just barfing like what mine is. Those RTP errors are coming out of a little junk switch that I have. It only takes about 6 gig to make it start occasionally barfing. And for the data community, you know, 2 errors every hour would be absolutely gorgeous. They wouldn't care. because there's protocols to do retrans. In video, we don't have that luxury.
So I have a related question. You know, a lot of what you say relates back to the design and the architecture of the switch backplane infrastructure architecture itself, whether or not it can handle the aggregate load from all those ports and such. Part of it relates to the port design itself. But you were showing your leader displays showing a video stream coming in and the timings and all that sort of thing. A nice little cross X display. That's with a single stream going across the link, correct?
That's one of my streams. I've got 4 going into the box. I picked one of the streams and was displaying that one stream against.
Okay, but
I can look at all 4.
Yeah,
I have to pick them one at a time. But yeah.
So what I'm particularly interested in is if you have, say, if those 4 streams, if they're going across a single link, across a single SFP, you got 4 streams going in parallel across a single SFP. They're completely different video streams. They're not just parallel 2202-7 streams, but they're different sources coming through, and they're going across the same trunk link to another switch, and then out to the various destinations where they go. How much do those streams interact with each other, and how much does it affect the stability of that timing on that display?
0. They do not interact with each other, unless unless you're overloading, like you said. What you'll see is, if I go back to one of my screens here real quick, and I look at actually IP measure, and I look at my packet jitter here. The top of the jitter window here, without the red in it, you should have a nice, consistent, very smooth flow if it's a hardware sender. Now we're getting into a lot of software senders. And a software sender is going to be all over the map. It already looks broke. I hated it the day software senders came out because it took half of my network troubleshooting away from me. Because you get a signature that you would get, and when the switch starts getting loaded, you start getting little hairs, little grass on top of this flow because it starts getting late on some packets because it's running out of real time to get those packets out in the order that they should and in the distance they should between each other. But unfortunately, a software sender does that to us from the get-go, unfortunately. And so we've all had to widen our buffers so that we can handle that. So, but yeah, they don't interact with each other unless something is broken. But that's where you need to learn your network and learn what is the normal characteristics and what does my network look like. And you don't get these like right now. I got a really late packet right there. It's hard to see the blue one, but the blue packet's there. And then you'll see a RTP error on top of it occasionally. But you get something that happens and it gets really, really late. And you can't take these views, like I'm looking at the last 2 hours. I can go out to 72 hours, or you can put it in virtually real time here. If I want to go here, I can go back to a very active moving graph, and if I change things enough, you'll start seeing changes. Let me see if I can. I have one video here that it doesn't like a lot. See if that one starts wiggling it or not. Yeah, that one's not doing a lot. I didn't have that set up for this demo, but I've had where I could actually increase the top of what this looks like by a lot by just loading the switch. And I've seen that where people have, you know, the other thing I've seen is in a SDI to IP converter where they're taking in 4, you know, SDI feeds and gumming out as a 10 gig feed. And they turn around and start throwing 3G in that. You can't have that many 3G links. You can only have 3G links in a 10 gig feed. So you should put that 4th on there, the encapsulator that you're using, ODs. And then it starts spitting all over the place.
Hey, Steve, John has his hand up for a question.
Yes, sir.
Well, I'll tell you, I don't know how I turned that on.
Okay.
Because I was trying to chat with my good friend Cindy and thank her for inviting me to join this. And I started typing a message to her, and all of a sudden all these windows started popping up. And I'm like, whoa, 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 wait a minute. This is all digital. This can't be going wrong.
Yeah, no, yeah. Well, you got to remember, digital's got 2 conditions, perfect and broke.
There you go. There you go. But I'm enjoying what I've jumped in late at, and my apologies for that. I wasn't aware of it. But what piece of equipment are we looking at here as a display?
This is a Leader LV5600.
Okay.
So this is the conventional unit, has a screen on it. You know, the little
Okay.
3 RU half rack wide, you know, conventional waveform monitor. We've got a 1 RU, same difference. But yeah, it does up to 4 HD streams at one time, and you can actually view all 4 at one time. So you can view SDI and IP simultaneously.
And Leader doesn't just that product line doesn't end at this type of form factor for test equipment, right?
No, it does not.
And didn't you guys did you get bought by, or did you guys buy somebody?
We bought Phabrix.
There it is. Yeah, that's what I was trying to figure out.
Yeah, and so
that's a pretty renowned.
There's the Phabrix box.
Ah, okay.
So this is the QXL, which is their 25 gig,
Gotcha.
25 gig box, which is used by a lot of engineering. It's not quite as detailed in pieces that normal operations has, and it's a lot more detailed in things that engineers love.
I think that's maybe the version up above that is what we have or are going to be soon receiving at Utah Scientific.
Yeah, probably.
Yeah. Good stuff, by the way.
Thank you.
Been a Leader fan since my first color bar generator. The portable, that is.
Appreciate that very much. Anybody else have any questions? And if you come up with more topics that you'd like to hear that are within the wheelhouse of Leader, I am more than happy to always do this.
You know, one of the things that I hear continually is are questions related to audio and how audio seems to be difficult in 2110. And it's that, okay, well, you know, we want to go ahead and do this and do that, and we can't. So what we do is we take all of our audio and we send it over to an audio mixer, and we demux it there and then remix it and send it back out from there. And I wonder if that was mostly a result of stuff before ISO 8 came around, or what? Because that audio, the audio capabilities of 2110 are just amazing.
Yeah.
In terms of capacity.
Yes.
It's like well, I read the sheets, and it's like okay, channels 1 through 8 of audio, and it's like, oh, okay, so it does 8 channels of audio. Well, wait a minute. Well, it doesn't really do just 8. It's how many flows do you want? And
yeah. Well, and you can get 64 channels on a flow on a 67.
Right.
So
if you choose a certain profile.
Yeah. Ours is an internal limitation inside the box, but we can do 16 channels, but we can break it up as 2 channels, 2 groups of 8, or 2 flows of 8 each, or 4 flows of 4. So we can do 4 flows of 4, 2 flows of 8, or 1 flow of 16.
Okay.
And that's per input, and there's 4 inputs.
And I guess coming from an industry that had, for so many years, had one speaker, it's probably not really too much to expect that we would have a huge knowledge base of what's going on with audio in 2110, because there's so much capability there. It's just ridiculous.
Yeah, yeah. And you know, on the backside, I mean, you get inside a facility and there's still a boatload of Dante going on though too. Dante has not gone away, and both of them use PTP, but unfortunately Dante uses version 1 PTP. We use version 2 for 2110, and they are not backwards compatible or cross compatible.
Right.
So we have to do some conversion on the Dante side to get it into 2110.
The advantage with Dante and why it's so popular amongst the audio community is because there's so many vendors providing so much equipment that is Dante compatible, and so it's really hard to avoid the all these other Ravenna and AES 67, all that kind of stuff. There just isn't the same breadth of vendor support for that stuff yet. So I'd love to see that change, but it's just not there yet.
Yeah, yeah.
No,
and it's a lot like we still got 5994. We don't need it, but we still got it.
Right. You know, one of the things we've looked at Utah Scientific is, okay, how many channels of Dante do you want to have coming into the router? It's like, well, I don't know, you know, we'll probably just buy one card and that should handle it. And it's like, well, I don't know that we're going to put our whole thrust into R&D for 17 cards a year of sales. I mean, really, it comes right down to brass tacks, down to that. And it's especially when you can go over to that store that's named after that river. What's that called? Amazon. So you can go over there and buy Dante stuff all day and all night long and have it in your hand in 10 minutes.
Yeah.
And it's not very expensive either, but yeah, so that's one of the things we've been faced with. And I think, Edward, your point is well taken, that there's a lot of people that are out there creating products with that device, and it's and share.
Yeah, and the Dante community has made devices that turn around and take Dante and flip it over to PTP version 2 and AES 67, and then it fits right into our workflow here. But yes, there is a little dividing line there.
But it does require another box.
Yes, it does.
Steve, in these 2110 implementations that you've seen, you know, video takes one path, audio takes a completely different. Where do you see them lining up, and where delay compensations managed for AV Sync?
In 2110 have not got there yet. That's kind of why I showed that one screen where, yeah, we can measure it for you. We can tell you where you're at. If you're inside a broadcast style company, your audio and video are going to be together on the same path from A to B. But if you're coming from, you know, remote production or production where, it's IP coming into the production switcher, then you're going to have two different paths, but they're both going to be tied to the same PTP source. So they're both going to have the proper timestamp in them. So all you need to do is look at that timestamp, and you know this audio packet goes with this video.
So right, but as things get processed differently in the video path and the audio path, you know, before it hits air, there's got to be some final time alignment.
Yeah. Yeah. Well, the one encapsulator I'm using happens to be actually from AJA. It gives me the ability to slide my audio and line my audio back up.
Okay.
So,
but shouldn't, unless I imagine if the audio was created along with the video, for example, a camera shot with a microphone that was recorded at the same time, that would all be timestamped with the same timestamp, and PTP and the buffering in the processing taking place, the slewing, if you will, in the switch would accommodate. No?
No, no, they'd be perfectly aligned together.
Right,
and
right.
If there is delays, and nothing's going to be perfect in IP, you're going to have packets moving back and forth. There's going to be this accordion effect of the packets, but that's where the PTP timestamp comes around and says, hey, once these get inside my buffer, I can now read them out of my buffer.
Yep.
And align those timestamps absolutely perfect once they get inside the box or whatever the device is.
So Larry, are you talking about dissimilar sources?
Sometimes yes, but I mean, even, if you go through video and you go through a split screen effect, that adds some latency on the audio side. If you go through a mixing console, you mix with other sources, there's other, processing.
Yeah. But if you look at the RTP timestamps, so the video is still going to have the correct RTP timestamps in it, even in a split.
Yep.
And when it comes out of the split, all you need to do now is put those audio packets back in time with the video from the RTP timestamps are in it, and you can go out from there.
Okay.
In time.
Steve, I love the.
That assumes that your video processor preserves the RTP timestamps for the packets going out as they were actually aligned with the RTP packets that came in, which oftentimes isn't the case. The other situation that can happen is if somebody's overdubbing audio into you from a different source, which has a completely different RTP source timing to it, and then all that falls apart. And you have to have some way of being able to adjust that back again. And it usually winds up being in a lot of buffer memory. With enough buffer, you can adjust forever, kind of thing.
But that's true about the losing or not passing that metadata.
Yeah.
But it almost sounds like what you're describing is an editing or a production effect, if you will, of adding that other channel.
I think even in live production, all the way through the chain, if you go, through your CalRec console, and then you go through, I don't know, up mixing, but then you hit loudness control before you go out to your final distribution. There's a bunch of processing in the chain, and it's a question of which timestamp do you preserve?
Yeah.
Is it the microphone from the camera? Is it the microphone from the announcer? Is, something else?
Yeah. Well, and if you're going to do it in the IP domain and in the 2110 AS67 wrapped domain, you need to actually do it with those timestamps, so that because the end device is going to put it back together based on those timestamps. It's going to say, here's the timestamp for my video, this frame. Here's the timestamps for my audio that go to this frame. And it's going to align those. So those need to be set correctly, leaving whatever device it is you're dealing with.
Yeah, one solution that has been proposed, and I assume that some manufacturers do this. If you've got a video processor, then it introduces some number of frames worth of a delay. Well, then it'll buffer the audio alongside with that's coming in through the stream, and then preserve those timing relationships, those RTP timestamp relationships between the audio and the video before it puts it back out again, to be able to keep that in line. But a lot of vendors may not take the time and the trouble to keep that in track, and that still doesn't solve the problem of the announcer coming on and voicing over the feed and these sorts of things. So there are some solutions for this, but they don't always work for all the different kinds of scenarios that you're going to run into.
Yeah, I know. Within what I have here, they aren't playing with the RTP timestamps; they're playing with the video inside the RTP timestamps and literally moving the video so the RTP timestamps always stay aligned, and they're just taking the audio and sliding what audio is in what RTP timestamp. And that way it hits my scope. My scope looks at the RTB timestamps of both, aligns the video, and it says, okay, well, here's your audio. And the audio, then you can look at it. But like I said, you do need to be careful, because I've ran into several devices that just for ease of use, they'll take the video stream in, they just FIFO it, they just take it, they don't look at the timestamps, get a package, they throw it on screen, they get the audio, they grab it, decode it, throw it on screen, and never align the two. And that can be dangerous.
That's why we call it engineering.
Yeah, and that's one thing, because at least I know with the leader scope here, the video will go away. If you muck up the RTD timestamps enough and you slew video off of PTP too far, you're outside of our buffer and we won't show you anything. Other devices, you know, it's like the old war with monitors. Monitors decode almost anything. You throw it into a box, go process it, and won't touch it. Just because, you know, the timing's so far off. And it's just, the monitor doesn't care. And, you know, the same thing with us. Since we do accurate audio video delay measurements, the only way we can do that is to look at those timestamps, put the packets together. Here's your video, here's your audio. Okay, here's your RTPs. Oh, where was the audio within that payload? And actually show it to you. And it'll do all 16 channels simultaneously.
You know, with PTP version 2, that's quite a move from where we started with sprocket holes. When you think about it, it really is. I mean, that's quite an upgrade.
Well, in the old days with sprocket holes, you would just advance your film by 6 sprockets.
There you go.
Exactly.
You know, one of the things that I ran into, I'm on my second fairly large 2110 build as an integrator, is your PTP clock quality is everything.
Yep.
And if you have so much jitter on your PTP, nothing will lock.
Exactly. And you know,
the other thing
PTP is very verbose, and you know, you run it through, hopefully, you know, something that's going to you know, a switch that will give you boundary clocking, but boundary clocking can only do so many within a switch before it gets overwhelmed, and once it gets overwhelmed, your PTP is going to pieces.
Well, and the other thing that I've run into is if you have a switch that is, you know, there's boundary clock switches and there's PTP aware switches. And sometimes that boundary clock switch, if it doesn't see a stable PTP clock, will go internal. Yes. And it'll generate its own internal clock. And then you have severe timing issues going on.
Yeah.
So.
Yeah, because it's a free run clock, and it's not a heated, you know, not a crystal oven controlled clock. So yeah, the drift's pretty bad.
But I think the other thing I learned is that really having GPS lock really improve. You know, a lot of these generators can have a pretty stable clock crystal in them, but the GPS lock improves the clock quality dramatically.
Yep.
Oh yeah, yeah. I mean, if you look at the clock class 6 down to clock class 248, that's the change between internal and GPS locked in PTP, and that's the lowest clock class they have. And that's even on a 1 ppm oven controlled crystal. So yes, there's a huge difference when it's GPS locked.
Alan, do you have your own integration firm that you're working on these things with?
I work for David Carroll and Associates in the Bay Area.
Oh, okay.
And we did, I helped Gary Schneider at LinkedIn. We did the 2022-6 systems. There are 5 sites there. And then we did a large installation at Dropbox headquarters in San Francisco. And now I'm working on a 4K IP system for a company that I can't mention. But it's the whole system's 4K, all IP. using this one's an Evertz EXE core in this particular setup with Magnum control. So yeah, we've gone through a lot of even this system. We've just finished up our interop lab, and we're getting ready to move the racks on site, and we've run into a whole slew of other issues that we always find. And this particular time has been NMOS control. Because the last system we actually didn't use any NMOS. We did all natting with everything, and that worked because we did all static SDPs with everything. Right. And this particular system, what we're finding is that a lot of manufacturers just haven't got NMOS down yet. So
that's very true.
Well, it's, I don't know how to say this exactly, but yeah, NMOS isn't technically a standard. It's an outline of a way to do something.
Right. Yeah, exactly.
So, but yeah, no, we've worked with it. We've got one site that is Evertz system control, and we've got 100 waveform monitors that are all being controlled off the NMOS.
Well, it's where you get one company trying to control another company's devices over NMOS, and that's where we've had, issues.
I don't know if you've looked at the NMOS stack, but you can find the same data in about 4 different threads. So different people go down a different thread to get the same data. And if nobody parses 100% of every thread you could possibly go down. And so that's where I've had to go in and tear things apart to see, well, we look at this thread and you're trying to go down that thread.
So Steve, do you recommend your device at all with Wireshark, or is Wireshark something that you don't ever even talk about with your customers, or do they wonder how it implements your stuff is implemented with a companion to Wireshark?
Well, so Wireshark is a gorgeous tool. Anybody doing 2110 better know it, but it's just static looking at captured packets.
Yep.
We do have, the ability to turn around and set up. Let me see. I can't see my menu because LinkedIn's in the way. There we are. I went to the wrong one. Give me a second here. Yeah, I guess it was on the right one. Oh, silly man. Capture and display, right there, PCAP. So we can do PCAPs straight off. I can give you the SDP file. So I can turn on PCAPs and look at port 1, port 2, or look at the Ethernet port if you want to look at PCAP of your Wireshark coming in, or I can just give you the SDP file off of what it is, or I can give you a standalone PTP PCAP.
I'm still twisting my decoder ring on PCAP. Which one is that?
That is the file format that is Wireshark.
Yeah, so Wireshark uses that.
Yeah, so PCAP is just their extension.
Yeah, you can use Wireshark is just a GUI interface to a netcap application. If you use a command line interface, netcap is just command line interface version of Wireshark, and everything's done off of PCAP capture files.
Yeah,
gotcha.
Yeah, it's a parser.
Yeah.
Another useful software tool that I use is TrackHound.
Yes.
TrackHound, and that shows you your grandmaster MAC address, and it shows timing delays, and it also shows your grandmaster, its hierarchy, because we've had systems where suddenly there's a device that came on, especially when you're mixing PTP version 1 and 2. Device will come on and go, hey, I'm going to be the master today.
Yes, yes. Well, you and I have had talks way long time ago about, never leave it at 127 and all the other things that you never do with PTP.
Yeah.
So you try to avoid that the best you can.
Steve, how long have you been with Leader?
About a year and a half.
Oh, okay.
So did 21 years at Tech.
Ah,
Been here for a year and a half.
So a newbie then.
Yeah. Just
Yeah, we used to
same job, different name.
we used to see Steve every year at the SMPTE conference down in Hollywood every year, and stop by his booth and have him show us his newest goodies every year.
right.
Yep.
So you worked with Quint Hanna at one point.
Oh yeah.
Okay, is this where my Zoom feed ends?
Yeah. We rode together enough that he lovingly occasionally called me his road wife.
Yeah.
TMI.
Oh, that flared up my allergies.
Yeah. Nah, I've known Quint for well over 15 years. So.
Yeah, no one wants to admit how long they've known him. So
Yeah.
I'm telling
that's
Katie.
fine.
I'm telling Katie you said that.
Hey, Katie's my friend now. Watch it.
All right, guys. Well, Steve, thanks. Steve and Bob, thank you for putting this on. This has been very helpful.
Good. I hope it was useful. I tried to present it, from a real world usable level, and let everybody see what was kind of going on from that angle.
Yeah.
So I hope I did that.
Well, I
Yeah,
got here late and I
absolutely.
learned a lot. So thank you.
All right. Thanks, everybody. Bye.
Very
Thank
much
you. It was great.
appreciated. Yeah. All right. Everyone have a good night.
Thank you very much. That was a good one.
Thank you.
Thank
Thank you very much.
Take care, guys.